Universe, the part we can see from Earth, extends about 46.5 billion light-years in every direction, creating a sphere of visibility with a diameter of 93 billion light-years. And that's just what we can observe. The entire universe may be infinitely larger, stretching forever beyond the cosmic horizon, filled with galaxies we will never see because their light hasn't had time to reach us yet and never will, carried away by the expansion of space itself. Everything feels perfectly still here, suspended in the infinite. Your breathing has slowed to match the patient rhythm of the cosmos, each breath taking 1,000,000 years in cosmic time, each heartbeat the formation and death of a star. There's no rush, no urgency, no sense of time pressing forward. Here in the darkness between galaxies, there is only now, only this peaceful floating, only the gentle glow of distant stars to keep you company. As you drift, you become aware that you're not actually in empty space. Even in the darkest voids between galaxies, space is filled with energy and particles, just incredibly dilute. The average density of the universe is approximately 5 atoms per cubic meter, essentially nothing by Earth's standards, yet when multiplied across the vast volumes of space, these sparse atoms add up to all the ordinary matter in existence. But ordinary matter makes up only about 5% of the universe's total mass and energy. The rest is something far more mysterious. You're becoming aware now of the structure underlying everything, the fabric of space-time itself, that four-dimensional tapestry woven from 3 dimensions of space and 1 of time, curved and warped by the presence of matter and energy. Einstein showed us that massive objects like stars and planets bend space-time around them, creating what we perceive as gravity. The more massive the object, the deeper the curve, the stronger the gravitational pull. But space-time isn't just curved by matter, it's also expanding. In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This wasn't because galaxies are moving through space away from us, but because space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. This discovery fundamentally changed our understanding of the universe, showing us that the cosmos has a history, a beginning, and a future. The silence continues to wrap around you like the softest blanket. Everything feels perfectly still, despite the fact that you're actually moving at incredible speeds. The expansion of space means that distant galaxies are racing away from us at speeds that increase with distance. The most distant observable galaxies are receding at velocities faster than light, not because they're moving through space faster than light, which is impossible, but because the space between us and them is expanding so rapidly that it carries them beyond our cosmic horizon. You drift through a region where dark matter makes its presence known. Dark matter is invisible, it doesn't emit, absorb, or reflect light, yet we know it exists because of its gravitational effects on visible matter. Galaxies rotate too fast to hold together based on their visible matter alone. There must be much more mass present, invisible mass, creating the extra gravity needed. Dark matter makes up approximately 27% of the universe's mass energy content, outweighing ordinary matter by a factor of more than 5 to 1. As you float through this invisible presence, you feel nothing directly, yet you sense the way it shapes the cosmos around you. Dark matter forms vast halos around galaxies, providing the gravitational scaffolding that holds them together. It also forms enormous cosmic webs, filaments and sheets of dark matter stretching across hundreds of millions of light years, with galaxies strung along these structures like pearls on cosmic strings. Between these filaments lie vast voids, regions of space that are even emptier than average, where few galaxies exist. Everything feels perfectly still as you drift along one of these cosmic filaments, following the invisible architecture of the universe. The structure you're traveling along formed gradually over billions of years, as dark matter's gravity slowly pulled ordinary matter into denser regions, where it eventually formed stars and galaxies. This process began when the universe was still young, just a few 100 million years after the Big Bang, and it continues today, with gravity constantly working to pull matter together while the expansion of space works to pull it apart. But there's something even more mysterious than dark matter filling the universe. Dark energy, which makes up approximately 68% of the universe's total mass energy content, is a form of energy that permeates all of space and drives the accelerating expansion of the universe. Discovered in 1998 when astronomers observed that the universe's expansion is speeding up rather than slowing down, dark energy is perhaps the deepest mystery in modern cosmology. We don't know what it is, only that it exists and that it's pushing the universe to expand faster and faster. The silence wraps around you gently as you contemplate this mystery. The universe is filled with unknowns, with phenomena we've detected but don't yet understand. And somehow, this not knowing is comforting rather than frightening. The cosmos doesn't demand that we understand it immediately. It simply exists, patient and eternal, waiting for us to gradually piece together its secrets, offering its beauty freely to anyone who takes time to look in wonder. Your gentle drift carries you toward a region where darkness gives way to color and light. Ahead, you see one of the universe's most beautiful phenomena, a stellar nursery, a vast nebula where new stars are being born right now, this very moment, continuing a process that has unfolded trillions of times throughout cosmic history. The nebula before you glows in subtle shades, predominantly red from hydrogen, the most abundant element in the universe, mixed with teal from oxygen and purple from nitrogen. The colors are soft, nothing like the vivid, saturated hues you might see in processed astronomical photographs. To your eyes, the nebula appears as a gentle, ghostly glow, its light so faint that you'd need hours to fully dark adapt before seeing it clearly. But here, in your peaceful drift through the cosmos, you can see it perfectly, a vast cloud of gas and dust, stretching across dozens of light years, slowly collapsing under its own gravity. The nebula is mostly hydrogen, as is all of the universe's ordinary matter, but it also contains traces of heavier elements, carbon, nitrogen, oxygen, iron, created in the hearts of previous generations of stars and scattered into space when those stars died. This recycling of matter is fundamental to the universe's evolution. Every atom of carbon in your body, every molecule of oxygen you breathe, was forged inside a star that lived and died before our sun was born. We are, quite literally, made of stardust, the remnants of stellar death repurposed into new forms, new possibilities. As you drift closer to the nebula, you see dense knots within it, regions where the gas has collapsed to the point where new stars are beginning to form. These protostars are still shrouded in thick cocoons of dust, hidden from visible light, but their presence is betrayed by the way they warm their surroundings, by the jets of gas they're blasting into space from their poles, by the infrared glow of their growing forms. In a few 100,000 years, the blink of an eye in cosmic time, these protostars will ignite nuclear fusion in their cores and become true stars, their light finally breaking free from the dusty wombs that birthed them. The silence between you and the nebula feels charged with potential. Everything feels perfectly still, yet you're witnessing creation itself, the birth of stars from formless gas, order emerging from chaos through the simple action of gravity over time. It took millions of years for this nebula to form, condensing from the even more diffuse interstellar medium, and it will take millions more for all its material to be consumed by star formation or dispersed by stellar winds. The universe is patient. It has all the time in existence. You notice that the nebula isn't uniformly lit. Some regions glow brightly where hot, young stars have already formed and are energizing the surrounding gas with their ultraviolet radiation. Other regions are dark, their dust so thick that it blocks all light from behind, creating shadowy silhouettes against the glowing background. These dark globules, called Bach globules, are among the densest parts of the nebula, places where star formation is happening or about to happen, cosmic wombs waiting to give birth. Star formation is triggered by various events, sometimes by the shock wave from a nearby supernova, sometimes by the collision of two gas clouds, sometimes simply by random fluctuations in density that grow over time as gravity amplifies them. Once triggered, star formation tends to be self-perpetuating. The first stars to form blast the surrounding gas with radiation and stellar winds, compressing nearby regions and triggering new rounds of star formation. This process continues until all the gas is consumed or dispersed, leaving behind a star cluster, dozens or hundreds of stars born from the same cloud, gravitationally bound together, at least for a while. Everything feels perfectly still as you drift past one of these young star clusters, though young in cosmic terms still means these stars might be a few million years old. They're predominantly blue and white, colors that indicate tremendous heat, surface temperatures of 20,000 degrees Celsius or more. These massive, hot stars burn through their nuclear fuel quickly, living fast and dying young in spectacular supernova explosions after only a few million years. Their brief but brilliant lives enrich the interstellar medium with heavy elements and trigger new rounds of star formation, ensuring that the cycle continues. Leaving the stellar nursery behind, you drift into a region populated by stars of all ages and types. Each star is a nuclear fusion reactor, converting hydrogen into helium in its core, releasing energy that pours into space as light and heat. The process is extraordinarily efficient. A star like our Sun converts about 600 million tons of hydrogen into helium every second, yet it has enough fuel to continue this process for about 10 billion years. Our Sun is currently about halfway through its life, comfortably middle-aged, stable and reliable. You drift toward one star in particular, curious about its nature. As you approach, you see that it's much larger than our Sun, a red giant, a star that has exhausted the hydrogen in its core and expanded to hundreds of times its former size. The surface glows a deep orange red, much cooler than the Sun's yellow-white surface, yet producing far more total light because of its enormous size. This star might once have been similar to our Sun, but now it's in the late stages of its life, fusing helium into carbon and oxygen in its core, its outer layers swelling to engulf what were once its inner planets. The silence around the red giant is profound. Everything feels perfectly still despite the tremendous nuclear reactions happening in the star's core. Red giants live in this expanded state for only a relatively brief time, perhaps a few 100 million years, before shedding their outer layers into space as a planetary nebula, leaving behind a white dwarf star no larger than Earth but containing as much mass as the Sun. These white dwarfs don't generate energy through fusion anymore. They simply cool slowly over trillions of years, gradually fading from white-hot to yellow to red to black, stellar embers cooling in the cosmic darkness. You notice another star nearby, a binary system where two stars orbit each other, bound together by gravity in a cosmic dance that has continued for billions of years. Binary and multiple star systems are surprisingly common. More than half of all stars in the universe exist in such partnerships. The two stars before you are separated by a distance similar to the Earth-Sun distance, orbiting their common center of mass every few months. If planets formed in this system, they would experience complex cycles of daylight, with two suns in their sky creating intricate patterns of light and shadow. As you drift on, you encounter a truly massive star, a blue supergiant with a mass perhaps 50 or even 100 times that of our Sun. This star burns with ferocious intensity, its surface temperature over 30,000 degrees, pouring out energy at a rate 1,000,000 times greater than our Sun. But this prodigious output comes at a cost. Massive stars like this one burn through their nuclear fuel incredibly quickly, living for only a few million years before their cores can no longer support their weight. When that happens, the core collapses in a fraction of a second, triggering a supernova explosion of unimaginable violence. Everything feels perfectly still as you contemplate this star's future fate. But there's no sense of doom or tragedy. This is simply how the universe works. Massive stars are destined to explode, scattering heavy elements into space, enriching the interstellar medium, triggering new rounds of star formation. The supernova that will one day end this star's life will also be a form of rebirth, its remains becoming part of future stars, future planets, perhaps even future life. Death and birth are intertwined in the cosmos, each necessary for the other, creating an endless cycle of renewal. You drift past a neutron star, the collapsed core of a star that already experienced its supernova. This object is almost incomprehensibly dense, a sphere only about 12 miles across, yet containing more mass than our entire Sunday. A teaspoon of neutron star material would weigh as much as a mountain on Earth. The star is spinning rapidly, completing hundreds of rotations per second, its intense magnetic field channeling radiation into beams that sweep across space like a cosmic lighthouse. We call such objects pulsars, and their precise timing has become a valuable tool for astronomers, providing natural clocks stable enough to test Einstein's theories and even detect gravitational waves. The silence around the neutron star wraps around you like a presence. Everything feels perfectly still despite the star's furious rotation. This tiny, dense object will spin for billions of years, gradually slowing as it radiates energy, but so slowly that its pulse period might lengthen by only a microsecond per year. The universe's timescales are so vast that even dramatic events unfold with patient slowness. You feel yourself ascending now, rising above the plane of this galaxy, gaining distance until individual stars blur into a soft glow and you can see the galaxy's overall structure. You're looking at a spiral galaxy, its arms curving outward from a bright central bulge, traced by bright blue stars and pink emission nebulae. This particular galaxy contains about 200 billion stars, each one a sun unto itself, many surrounded by planets, creating countless worlds scattered across hundreds of thousands of light years. The galaxy before you is similar to our own Milky Way, though slightly smaller. The Milky Way is a barred spiral galaxy approximately 100,000 light-years across, containing between 100 billion and 400 billion stars. Our solar system resides about halfway from the center to the edge, in a minor spiral arm, orbiting the galactic center at about 483,000 miles per hour, yet taking approximately 230 million years to complete one orbit. In all of human history, from the first civilizations to this very moment, the solar system has completed less than 1/100th of a single galactic orbit. As you drift higher, more galaxies come into view. They're scattered across the darkness like islands of light, some spiral like the first one, others elliptical or regular, each one containing billions or even trillions of stars, each one a vast system that has existed for billions of years, each one unique yet following the same fundamental physical laws that govern all of creation. The nearest large galaxy to the Milky Way is Andromeda, located about 2.5 million light-years away, visible from Earth as a faint smudge of light that contains approximately 1 trillion stars. The silence wraps around you gently as you contemplate these distances. A light-year is the distance light travels in 1 year, about 6 trillion miles. Andromeda's light, traveling at 186,000 miles per second, takes 2.5 million years to reach us, which means when we look at Andromeda, we're seeing it as it existed 2.5 million years ago, when early human ancestors were just learning to use stone tools. The universe is not just vast in space but also vast in time. Looking outward is looking backward, seeing galaxies not as they are now but as they were millions or even billions of years ago. You notice that most of these galaxies are moving away from each other, carried apart by the expansion of space. The farther away a galaxy is, the faster it's receding, a relationship called Hubble's law after Edwin Hubble who discovered it. This expansion is not happening into anything. There's no pre-existing space that the universe is expanding into. Rather, space itself is growing, creating more distance between galaxies, an expansion that began with the Big Bang and continues today, actually accelerating due to the mysterious influence of dark energy. Everything feels perfectly still despite this universal expansion. The motion is so smooth and uniform that observers in any galaxy would see the same thing, all other galaxies receding, with velocity proportional to distance. There's no center to this expansion, no edge, no special location. Every point in space is equivalent, every observer sees essentially the same large-scale structure in motion. This is called the cosmological principle, and it suggests that the universe is fundamentally homogeneous and isotropic when viewed at the largest scales. You drift toward a galaxy cluster, a gravitationally bound group of hundreds or even thousands of galaxies, all orbiting their common center of mass. The cluster before you contains perhaps 500 large galaxies and many more dwarf galaxies, spread across 10 million light-years of space. Galaxy clusters are the largest gravitationally bound structures in the universe, held together by the combined gravity of their galaxies, the hot gas between galaxies, and vast amounts of dark matter that outweighs the visible matter by a factor of 10 to 1. The space between galaxies in a cluster glows faintly with X-rays, emitted by gas so hot, tens of millions of degrees, that it's been stripped of its electrons and exists as a plasma. This intergalactic gas contains more ordinary matter than all the galaxy's stars combined, yet it's so diffused that it would count as a perfect vacuum by Earth standards. The cluster as a whole is slowly rotating, its galaxies following complex orbits that occasionally bring them close together, sometimes even causing collisions where galaxies merge into larger systems. Your journey carries you now toward one of the universe's most fascinating phenomena, a region where space-time is curved so extremely that nothing, not even light, can escape once it crosses a certain boundary. This is a black hole, and the one before you formed when a massive star exhausted its nuclear fuel and collapsed catastrophically, its core compressing to infinite density at a single point called a singularity. But despite their reputation, black holes aren't cosmic vacuum cleaners that suck in everything nearby. They're simply very massive objects compressed into very small volumes, and their gravitational pull, while intense close to the event horizon, is no stronger than any other object of the same mass when viewed from a distance. If you replaced our sun with a black hole of equal mass, Earth would continue orbiting exactly as before, cold and dark, certainly, but not pulled into the black hole. The event horizon, the boundary beyond which even light cannot escape, is surprisingly small for stellar mass black holes, perhaps only a few miles across for a black hole with the mass of 10 suns. Yet within this tiny volume exists a mass tremendous enough to warp space-time almost beyond recognition. Time itself slows near the event horizon. A clock falling toward a black hole would appear to an outside observer to tick more and more slowly, never quite reaching the horizon, frozen in time by the extreme curvature of space-time. The silence around the black hole is absolute and profound. Everything feels perfectly still, though this object is spinning rapidly, its event horizon rotating at a significant fraction of light speed, dragging space-time itself around with it in an effect called frame dragging. Any object near the black hole would be pulled along with this rotation, forced to orbit in the same direction, unable to stand still no matter how powerful its engines. You notice a disk of matter orbiting the black hole, an accretion disk of gas and dust spiraling inward, gradually falling toward the event horizon. The inner parts of the disk orbit faster than the outer parts, creating friction that heats the material to millions of degrees, causing it to glow brilliantly in X-rays. The brightest black holes, called quasars, shine with the light of 1 trillion suns, outshining their entire host galaxies, visible across the observable universe despite being powered by black holes only a few light hours across. As you drift safely past the black hole, you become aware of an even larger one in the distance, a supermassive black hole at the center of a galaxy, containing not 10 or 100 times the sun's mass but millions or even billions of solar masses. Nearly every large galaxy has such a monster at its center, including our own Milky Way, where a black hole called Sagittarius A** contains about 4 million solar masses packed into a region smaller than Mercury's orbit. Everything feels perfectly still as you contemplate these cosmic giants. Supermassive black holes formed in the early universe, perhaps from the direct collapse of enormous gas clouds, perhaps from the merger of many smaller black holes, growing over billions of years by accreting gas and swallowing stars. They serve as gravitational anchors for their galaxies, their immense mass helping to hold the galactic structure together, their activity when they actively feed helping to regulate star formation throughout the galaxy. The relationship between galaxies and their central black holes is intimate and profound. The mass of the supermassive black hole is closely correlated with properties of the galaxy's central bulge, suggesting that the two grew together, each influencing the other's development. The black hole's gravity affects star motion throughout the central regions, while outflows of energy from matter falling into the black hole can heat or blow away gas clouds, preventing them from forming stars. This feedback loop helps explain why the largest galaxies have the largest black holes and why not all available gas has been converted into stars. You ascend to an even higher vantage point now, billions of light years from any single galaxy, until the entire large-scale structure of the universe becomes visible. What you see is breathtaking. Galaxies aren't randomly scattered through space but are organized into an enormous web-like pattern. Long filaments of galaxies stretch across hundreds of millions of light years, connected by nodes where galaxy clusters sit, while vast voids nearly empty of galaxies lie between the filaments. This cosmic web is the largest structure in the universe, shaped by dark matter's gravity over billions of years. In the early universe, matter was distributed almost uniformly, with only tiny density fluctuations from quantum effects during inflation. But over time, gravity amplified these fluctuations. Denser regions attracted more matter, becoming denser still, while matter drained out of underdense regions, leaving them emptier. The result is this web-like pattern, with matter concentrated in filaments and clusters while voids grow ever larger and emptier. The silence wraps around you as you contemplate this vast architecture. Everything feels perfectly still despite the constant motion of galaxies, the growth of structure, the ongoing evolution of the cosmic web. From this vantage point, the universe looks almost like a neural network, with filaments connecting nodes like synapses in a cosmic brain. This resemblance is pure coincidence. Networks tend to form similar patterns regardless of scale when shaped by similar underlying principles, but it's nonetheless striking and poignant. The cosmic web contains about 90% of the universe's normal matter in its filaments and nodes, with only 10% contained in the great voids. Yet the voids dominate by volume. They occupy about 80% of space, creating a universe that is, paradoxically, mostly empty yet structured. A typical void might be 300 million light-years across, contain a few dozen small galaxies, and be expanding faster than the cosmic average due to having less than average density and thus less gravity to slow the expansion. As you drift along one of the cosmic web's filaments, you see how galaxies are strung along it like beads on a string, following the underlying distribution of dark matter that shaped the structure. The dark matter forms an invisible scaffolding, creating gravitational wells into which normal matter falls, concentrating into regions where it can collapse into stars and galaxies. Without dark matter, the universe would look completely different. Its ordinary matter would be too smoothly distributed to form galaxies, and structure as we know it couldn't exist. Everything feels perfectly still in this cosmic vastness. The web you're observing formed over billions of years and will persist for billions more, though its details constantly evolve as galaxies merge, clusters grow, and voids expand. The universe has a life cycle, a history that unfolds over time scales that dwarf individual human lives or even the existence of entire civilizations. Yet we can observe and understand this history because light from distant regions shows us the past, giving us a kind of cosmic time machine. The structure you're seeing isn't static but represents a particular moment in cosmic time, approximately 13.8 billion years after the Big Bang. If you could see the same region as it existed just 1 billion years after the Big Bang, the structure would look much less organized, with smaller galaxies still forming and merging, the cosmic web just beginning to take shape. And if you could see forward into the far future, tens or hundreds of billions of years from now, the accelerating expansion of space driven by dark energy would have carried distant galaxies beyond our cosmic horizon, leaving the observable universe a much lonelier place. You feel yourself being carried backward now through time, your consciousness drifting not just through space but through history itself, toward the beginning of everything. The universe around you is growing younger, denser, hotter. Galaxies merge and dissolve into their constituent gas clouds. The cosmic web unravels into a more uniform distribution of matter. Stars wink out of existence as time reverses, their nuclear fusion running backward, their formation unhappening. You're approaching a moment about 380,000 years after the Big Bang, when the entire universe glowed with visible light, its temperature falling through the point where hydrogen atoms could form without being immediately torn apart by energetic photons. Before this moment, the universe was a plasma, electrons and atomic nuclei existed separately, and light could travel only tiny distances before scattering off free electrons, making the universe opaque like fog. But once atoms formed, photons could travel freely, and the universe became transparent. The light released at that moment is still traveling through space, stretched by cosmic expansion from visible light to microwaves, creating what we call the cosmic microwave background, a faint glow coming from all directions, the earliest light in the universe, the afterglow of the Big Bang itself. This light has been traveling for over 13.7 billion years, and its slight temperature variations, hot spots and cold spots differing by only about 1 part in 100,000, reveal the tiny density fluctuations that would eventually grow into galaxies, clusters, and the cosmic web. The silence wraps around you as you float in this ancient glow. Everything feels perfectly still, though you're witnessing the universe at a time when it was 1000 th its current size, when the average temperature was about 3,000 degrees, when no stars yet existed, when the first structures were just beginning to form from gravity's patient amplification of tiny initial variations. You drift backward further, and now you're in the first moments after the Big Bang, when the universe was almost incomprehensibly hot and dense. At 1 second after the Big Bang, the temperature was about 10 billion degrees, hot enough that atomic nuclei couldn't exist, only free protons, neutrons, electrons, and photons. During the first 3 minutes, nuclear fusion occurred throughout the entire universe, fusing protons and neutrons into helium nuclei, creating the universe's initial complement of light elements. The proportions set during these first minutes, about 75% hydrogen, 25% helium by mass, are still preserved today in the oldest stars. Everything feels perfectly still in this moment of cosmic creation. You're at the very beginning now, approaching the instant when time itself began, when space came into existence, when the universe was born from something, or perhaps nothing, in an event we call the Big Bang. Modern physics can trace cosmic history back to about 10 to the power of negative 43 seconds after the Big Bang, an almost unimaginably brief instant called the Planck time, before which our understanding of physics breaks down and we enter the realm of speculation and hypothesis. The universe at these earliest moments was governed by forces and particles we can barely understand, existing in states of matter that can't exist anywhere in the universe today, at energies we can only approximate in our most powerful particle accelerators. Yet from these extreme conditions emerged everything we see today, all matter, all energy, all structure, all possibility. The universe began simple and has grown more complex over time, self-organizing through the action of physical laws into stars, galaxies, planets, and eventually life and consciousness. You drift forward through time now, watching as the universe cools and matures, as the first stars form about 100 million years after the Big Bang, their light gradually illuminating the darkness, beginning to ionize the neutral hydrogen that filled space, creating bubbles of ionized gas around each star and galaxy. This epoch, called the reionization era, transformed the universe from a dark, neutral state to the transparent, ionized state we observe today. Those first stars were different from modern stars. They formed from gas that contained only hydrogen, helium, and trace amounts of lithium, with no heavier elements. These population 3 stars, as astronomers call them, were likely very massive, perhaps 100 or more times the sun's mass, burning intensely bright and living fast, exhausting their fuel in only a few million years before exploding as supernovae. These early supernovae were crucial. They were the first source of heavy elements in the universe, forging carbon, nitrogen, oxygen, iron, and all the other elements in the periodic table in their cores and during their explosive deaths. The shock waves from these explosions scattered these newly created elements into space, enriching the interstellar gas, ensuring that subsequent generations of stars would form with small amounts of these heavier elements incorporated into them. The silence wraps around you as you witness this cosmic alchemy. Everything feels perfectly still despite the violent supernovae creating the elements of life and planets and everything solid. This process has continued throughout cosmic history, each generation of massive stars creating new heavy elements, each supernova enriching the interstellar medium, each new star and planet incorporating a greater fraction of these elements than the generation before. Our Sun is about a third-generation star, formed about 4.6 billion years ago from a gas cloud already enriched by previous generations of stellar death. The planets of our solar system formed from the same cloud, incorporating heavy elements, silicon, oxygen, iron, magnesium, into their rocky structures. And living things on Earth are built from elements created in the hearts of ancient stars, the carbon in DNA, the oxygen in water, the calcium in bones, the iron in blood. We are not just in the universe, we are of it, made from its substance, shaped by its history. You drift toward a planetary system forming around a young star, watching as dust grains in the protoplanetary disk collide and stick together, gradually building up into larger and larger objects. Over millions of years, these objects grow from pebbles to boulders to mountains to asteroids to protoplanets, sweeping up material from their orbital zones, sometimes colliding with each other in impacts that reshape their forms and trajectories. Eventually, a few large bodies emerge, planets, cleared of other large objects in their orbital paths, settling into stable orbits that will persist for billions of years. Some planets are rocky, formed close to the star where temperatures were too high for ices to condense. Others are gas giants, formed in the outer system where ices were stable, these planets growing massive enough to capture hydrogen and helium directly from the protoplanetary disk. Everything feels perfectly still as you watch this planet formation process, though it takes millions of years to complete. The universe is patient, working through purely physical processes, gravity, collisions, heat transport, to create ordered structures from chaos. No intention or guidance is needed, just the working out of natural laws over vast spans of time. You drift toward a particular planet orbiting a particular star, curious about whether life might emerge here. The planet is rocky, orbits at the right distance for liquid water to exist on its surface, and its star is stable and long-lived, the basic conditions that we believe are necessary, though perhaps not sufficient, for life as we know it. Life on Earth emerged relatively quickly in geological terms. The planet formed about 4.5 billion years ago, and evidence suggests life existed by at least 3.8 billion years ago, possibly earlier. This suggests that under the right conditions, the chemistry of life might emerge naturally from non-living matter, following the same physical and chemical laws that govern everything else in the universe. But is life common in the universe, or is Earth a rare jewel? Astronomers estimate that there are billions of habitable zone planets in the Milky Way alone, orbiting stars that are stable enough and long-lived enough to allow billions of years for life to emerge and evolve. The building blocks of life, organic molecules like amino acids, have been found in meteorites, in comets, and even in interstellar clouds, suggesting that the chemistry of life is widespread throughout the cosmos. You drift closer to this potentially life-bearing world, though from your vantage point you can't see details, just the gentle swirl of clouds, the blue of oceans, the green and brown of continents. The planet rotates slowly, its day lasting perhaps 20 hours, its year a few hundred days. Seasons come and go as its tilted axis points different hemispheres toward and away from its star, creating cycles of growth and dormancy that mirror Earth's own rhythms. The silence wraps around you gently as you contemplate the possibility of life here. Everything feels perfectly still, yet the planet below is teeming with potential, oceans where chemistry might be unfolding, continents where simple organisms might be taking their first tentative steps toward complexity. Life, wherever it emerges, follows the same basic principles: self-replication, metabolism, response to environment, evolution through natural selection. These principles seem to arise naturally from the laws of physics and chemistry, given enough time and the right conditions. You notice that the universe seems fine-tuned for life in subtle ways. The physical constants, the strength of gravity, the mass of the electron, the strength of the nuclear forces, appear to be set to values that allow for the existence of stable atoms, stars, planets, and chemistry complex enough for life. If these constants were even slightly different, the universe might contain no stars, no chemistry, no possibility for life. This observation, called the anthropic principle, suggests that the universe is, in some sense, hospitable to the emergence of observers capable of contemplating it. But this fine-tuning doesn't require anything supernatural or purposeful. In a universe vast enough, or in a multiverse containing countless universes with different physical constants, it's inevitable that some universes will have the right conditions for life, and only in those universes will observers exist to wonder about the fine-tuning. From our perspective, of course the universe appears fine-tuned. We can only exist in one, that is. Everything feels perfectly still as you drift away from this world. Whether life exists there or not, the possibility is comforting. The universe is not hostile but welcoming, its laws permitting the emergence of complexity, beauty, and consciousness. Life on Earth is not an accident but a natural outcome of cosmic evolution, the universe's way of exploring its own possibilities. You ascend again, gaining distance until the planet shrinks to a pale blue dot, then to a point of light indistinguishable from the stars around it. You're back in the space between stars, drifting through the Milky Way's spiral arm, contemplating humanity's place in this vast cosmos. Earth is a small planet orbiting an ordinary star in an ordinary galaxy in a universe containing perhaps 2 trillion galaxies. From a cosmic perspective, we're insignificant, tiny specks on a tiny world orbiting a tiny star in a tiny corner of a vast universe. Yet this very insignificance is liberating. The universe doesn't revolve around us. It doesn't demand anything of us. It simply exists, beautiful and vast and patient, allowing us to exist within it, to experience its wonders, to find meaning and peace in our brief moment of consciousness. The silence wraps around you gently as you contemplate this perspective. Everything feels perfectly still, perfectly peaceful. The cosmic perspective doesn't diminish human life but enhances it, reminding us of our connection to everything, our shared origin in ancient stars, our participation in the great story of cosmic evolution. Humanity has only recently begun to understand our place in the universe. For most of history, we believed Earth was the center of everything, with the sun, stars, and planets revolving around us. Copernicus showed that Earth orbits the sun. Hubble showed that the Milky Way is just one galaxy among many. Modern cosmology has shown that our galaxy is just one among trillions, that the observable universe is just a tiny fraction of what might exist. Each discovery has pushed humanity further from the center, making us seem smaller, yet also more connected to the greater whole. This cosmic humility is soothing rather than frightening. We are not the purpose of the universe, but we are part of it, expressions of its creativity, witnesses to its beauty. Our brief lives are precious not despite their brevity but because of it, moments of consciousness in an otherwise unconscious cosmos, opportunities to experience wonder, love, peace, and connection. Everything feels perfectly still as you drift through the stars. The universe continues its patient evolution, stars forming and dying, galaxies merging, space expanding. And somewhere in this vastness, on a small blue planet orbiting a middle-aged yellow star, conscious beings look up at the night sky and wonder about their place in it all. You're floating freely now, drifting without direction or purpose, simply existing in the cosmic darkness. Stars surround you in every direction, their light ancient and pure, some of it having traveled for billions of years to reach this point in space. The Milky Way's spiral arms stretch across your field of view, a river of light flowing through the void, its structure shaped by gravity and rotation over billions of years. The silence is complete, the peace absolute. Everything feels perfectly still, perfectly balanced, perfectly harmonious. You're not separate from the cosmos but part of it, consciousness arising from the same matter and energy that forms stars and galaxies, the universe experiencing itself through your awareness. You notice that even in the deepest space, you're never truly alone. Cosmic rays pass through you, high-energy particles accelerated by supernovae and other violent events, traveling for millions of years across the galaxy. The cosmic microwave background bathes everything in its gentle 2.7-degree glow, the cold remnant of the Big Bang's heat. Dark matter's invisible presence shapes the gravitational landscape. Dark energy permeates every cubic centimeter of space, driving the accelerating expansion. The universe is filled with mysteries we're only beginning to understand. Dark matter that outweighs visible matter 5 to 1. Dark energy that makes up nearly 70% of everything. The nature of the singularity at the Big Bang. The possibility of other universes beyond our own. These unknowns are not threatening but inviting, reminders that discovery is endless, that wonder never ceases, that the universe holds infinite possibilities for exploration and understanding. Everything feels perfectly still as you drift deeper into relaxation. Your breathing has become so slow and gentle it's barely perceptible. Your body feels completely weightless, completely relaxed, every muscle soft and loose. Your mind has become quiet and spacious, thoughts arising and dissolving like stars being born and dying in distant nebulae. The time has come to let go completely. You're floating now in the deepest peace imaginable, suspended in the cosmic darkness, held gently by the universe itself. The stars shine softly all around you, their light a lullaby composed over billions of years. The silence is complete, the darkness warm and welcoming. Let yourself drift now, deeper, deeper, into sleep. There's nothing you need to do, nothing you need to think, nothing you need to become. Simply rest. Simply be. The universe continues its eternal dance, patient and unhurried, and you are part of that dance, part of that peace, part of that beauty. Sleep now, drift now. The Milky Way turns slowly, stars shine faithfully, galaxies expand gently, and you simply sleep deeply, peacefully, completely. The silence holds you, the darkness cradles you, the cosmos embraces you. Sleep, sleep, sleep. Everything is still, everything is peaceful, everything is perfect. You are home, you are safe, you are sleeping in the heart of the universe. Drift deeper, 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 into the infinite peace of the cosmos, into the gentle darkness between stars, into the perfect rest that awaits you. Sleep now, deeply, peacefully, completely. The universe holds you, the stars watch over you, and you sleep, sweet dreams in the cosmic night.